to the seminar. Our speaker is Clementine Bechet, and she did her thesis at Lyon. She did her thesis in wavefront reconstruction, and now she's working at ESO. And she keeps working on wavefront reconstruction, and we have been collaborating with her, studying the algorithms for the European ELT. And she's going to give a talk on the subject she's working on now, that is inverse problem approach in adaptive optics for the ELT.
Thank you, Isa. So, good morning, everybody. I'm going to talk about inverse problem approach in adaptive optics for the extremely large telescopes. So I guess some people are not experts of adaptive optics, so I try to present first the context and the problems of adaptive optics for the European ELT, and then I will enter more in details about my subject, wavefront reconstruction using an inverse problem approach. And I will show you some results we obtained with the wavefront reconstruction algorithm, and also trying to simulate a full closed-loop adaptive optic on a very large telescope like the European ELT. So first, the scientific goals for the European ELTs are really ambitious. Due to the very large primary mirror, we expect to observe extrasolar planets and Earth, to study extragalactic black holes and resolve stellar populations. And another major aim is to study the formation, evolution, dynamics of the galaxies of a high redshift. So the gain of the European ELT is to have a great sensitivity with a gain of 3 to 5 magnitudes with respect to what is possible with the VLT. And also, because of the diffraction law, the resolution is increased using a bigger mirror, so we can have unavailable resolution, angular resolution, reaching 2 milliarcs again in the visible. But this is theoretic because the ground-based telescopes suffer from one disease, which is the turbulent atmosphere of the Earth. And so when you observe one star, the wavefront, just to remind what's adaptive optics, when you observe one star, the wavefront goes through the turbulence of the atmosphere and is perturbed. And these disturbances produce a loss in the angular resolution of the image of 300 in the visible compared to what you would have if you had not the atmosphere. So it's a great loss. And the aim of the adaptive optics is to analyze the perturbation of the wavefront with a wavefront sensor. Okay, with a wavefront sensor here. And for example, here is a Shackartman wavefront sensor. So if the wavefront were flat, you would have small images in the subapertures here, which are all centered. And since there are perturbations due to the atmosphere, these spots are moved, and then you can acquire the data to get the slopes of the wavefront above the aperture of the telescope. And from this data, you try to, oops, what happened? Okay. Yeah. Okay. You can try to reconstruct the perturbation of the wavefront. Yeah, here. And this is the step of reconstruction and control for the adaptive optics system. And from this, you control a deformable mirror to compensate the perturbation of the wavefront in real time. And this provides you diffraction-limited images on the science camera. So this is the principle of the closed-loop adaptive optics. And it allows you to retrieve the diffraction limited resolution. A big issue of adaptive optics is that usually astronomers want to observe faint objects, and the closed-loop adaptive optics must run on bright guide stars because it needs a signal to be close. And so if one wants to observe a faint object, it has to have a bright guide star nearby, because if one looks at another object, the turbulence for the wavefront sensing is not the right one. Here you have a turbulence which is not the one you are correcting for on the guide star. So this produces aberrations still on the science camera. It's called anisoplanetism. It means that if you go away from the guide star, you don't have the right correction. And it's a major issue. It provides you an angle of a few arc seconds around a few arc seconds around the bright guide star. So this is a major issue if you want to have wide field observations, and also if you want to observe with faint objects, which is the aim of the ELT due to his large primary mirror. So for this, many adaptive optics systems and concepts have been designed for the European ELT, and they all have strange names like SCAO, XAO, LTAO, MCAO, MOAO, JLAO, which are all a trade-off between the field of view you want to correct for and the quality of the correction. As soon as you increase the field of view you are correcting for, you will degrade the quality of the correction. So actually, at the moment, to astronomers, only single-conjugate AO, classical AO, is available. And only 3 of these have been experimented on SCAI, which is MCAO, multi-conjugate, adaptive optics with the demonstrator of ESO, MAD, and also ground layer AO, which has been also tested with MAD. So there is a major difficulty to invent all this adaptive optics system for the European ELT, because we want them to work, and it's just a challenge. So just to have a fast explanation of this AO system. So here is the classical AO system you may know, which has, what's that? Which is just one guide star, and you look at the wavefront and you are correcting on axis. But then, if you look at the ground layer AO, which is the one who provides the biggest field of view corrected, but since it goes up to 10 arc minutes of correction, the correction is very low, and you are only correcting for the ground layer above the telescope, which is where the major turbulence is concentrated. For this, you use several guide stars in the field of view you want to correct for. And if you combine the wavefront perturbations coming from all these guide stars, they have in common this ground layer perturbation. So you correct from this using the correlations of all these perturbations. From this, if you want to improve the correction, you will try to correct from the ground layer and also high altitude layers. And for example, you can do it using one or several deformable mirror conjugated to other altitudes of turbulence, which is here in that case star-oriented MCAO. The multi-object AO is much more a challenge. It expects to correct several objects in a very large field. Also, can be larger than 5 arc minutes, but it will only correct in the direction of the objects you want to to correct for the galaxies. So you will analyze the perturbations of a very, very large field and correct only in a given direction very well, much better than MCAO. And you expect to be able to correct like 20 galaxies at the same time, but in different directions. And for this, what will be indispensable is a laser guide star, because people will observe in faint fields, and there will not be enough bright guide star to provide a good adaptive optic correction. So the principle of the laser guide star is to generate an artificial guide star with laser. You project on the sodium layer of the atmosphere, and it creates an artificial guide star. But since these stars are at a finite distance of the telescope, you have a cone effect, and you don't have exactly the same turbulence sensed than you would have when you look at a star at infinity. So you have to combine the data coming from all the directions to be able to reconstruct the cylindrical volume that perturbs your object at infinity. That's why you have to build a tomographic reconstruction of the wavefront. So the wavefront reconstruction is a key point to develop the adaptive optics of the European ELT. And I will enter more in detail now in what consists and how to make a wavefront reconstruction. So here is an example, again, of the most famous wavefront sensor, which is the Shack-Hartmann wavefront sensor. So with the wavefront you observe, so here is an image, a simulated image of wavefront perturbations over the pupil of the telescope. So like this here, and you sense the slopes, the gradients, local gradients of this image on the wavefront sensor. You have the displacements in X and Y locally. And from your data, you want to reconstruct the physical parameters, which are here, all these perturbations. So this is an inverse problem. From the data, you have a model of your wavefront sensing process, and you want to recover the physical parameters. For this, what we do is we model the wavefront sensing process with a linear model. And the reconstruction consists in inverting this process, this model process. And in this case, it consists in a two-dimensional integration from the slopes to the wavefront. And this is a nil-post problem. It means that there is an infinity of estimation possible of the wavefront, so you have to find which one will be the most, the nearest from the true wavefront. So it's not that easy. So when you use equations to do this, you model the data as coming from the linear model of the wavefront sensor, applied on the perturbed wavefront, and the data are noisy. And what you want to obtain is a reconstruction of the wavefront. W. So you obtain this estimated wavefront with a linear reconstructor. You apply on the data, and R is the linear reconstructor we are looking for. When at the beginning of the adaptive optics, usually people develop the least square, Gauss least square classical inversion to do this. And this consists in minimizing the square difference, well, it's Gaussian least square, the square difference between the model and the data. And what we can do is do better, taking into account the statistics we know about the noise of the wavefront sensing process and about the wavefront perturbation. since the turbulence is a stochastic process. Yeah. Is a matricial? No. Yeah. Inside S. S is a matrix. Okay. You can approximate the derivative, local derivative, with a finite difference. Yes. Usually the most used model for the Shakart-Man wavefront sensor is that you try to reconstruct locally the perturbations of the wavefront. And for this, on the subaperture where you are measuring the displacement of the spot, it's just the half sum of the difference between the sides of the subaperture. Well, it's just a finite difference relation, linear combination. So this allows you to estimate the wavefront on several points on the aperture. It's a local formulation. So this is a vector. Where is it? Yeah. This is a vector, and this is a linear model, usually represented as a matrix. And this is the wavefront. So as soon as it's a matrix, but it's not an invertible matrix. So you can approach the inverse by this formula with a pseudo-inverse here. But this will give you the minimum norm of the wavefront, the wavefront of minimum norm, which correspond to this data. But what you can do is do better than this pseudo-inverse, is using the statistics of the wavefront perturbations and of the noise to build a maximum a posteriori reconstruction. And this is just a Bayesian estimator of the wavefront from the data. And thanks to this, this is obtained using the covariance of the wavefront parameter and the covariance of the noise, which you suppose a priori. And this allows you to have something invertible here. You finally end with a matrix here, which is invertible. So you have a unique solution of this problem. And this gives you an optimal reconstruction in the statistical point of view, because it minimizes the variance of the error you make in your reconstruction. And it also provides you the optimal trade-off between a bias you will introduce in your reconstruction because of the regularization on the wavefront. Means that you will suppose that your parameters, your wavefront perturbation cannot be anything. They must follow the turbulence statistics. And so you constrain your estimation to follow these statistics. That's what it does. So with this constraint, you bias your estimation. And the maximum a posteriori reconstruction gives you the best trade-off between the bias you introduce with the regularization and the noise propagation you introduce with the term which is linked to the data here. Yeah. Yeah. Yes, that's it. That's a special difficulty. There are several approaches, and I'll talk about closed loop later, but I can already tell that what we do is to try to conserve the statistics of the open loop case, and we just reconstruct pseudo open loop data, which means that we know that in closed loop we have done this. We have put this perturbation. And so we add it to the data to subtract it from the data. Then we have an estimation of what it is in open loop. Is it clear? No. Okay. Yeah, you know what you have done with your mirror. You know the commands. So you know what is the perturbation you have introduced to you. And so you get the closed loop data, which is the residual, the difference between the two. And what you do is that you add what you have done and it's canceling it. So since you canceled it, you have an estimate of the open loop ones, open loop data. And you apply the reconstruction on the pseudo open loop data. But it's not, this is not done on the current AO system. What is done in the current AO system, usually they use the Kolmogorov statistics, but they just turn it down just to make the regularization less important because it doesn't correspond to what they are looking at, since it's residual perturbations. I'll try to explain why this reconstruction is optimal for the special case of the extremely large telescope. It's because when you try to when you simulate the wavefront error, the wavefront reconstruction error, well, here it is normalized by the wavefront perturbations you have at the beginning coming from turbulence. But when you have a system which has more and more degrees of freedom, which will be the case with the 42-meter telescope, with the MCAO system, each time you want more precision, extreme AO system, you will increase the number of data you will get. And since you have more data, can't understand why. Since you have more data, you also have a larger difference between what would give you the Gaussian least square performance, a larger error, and what gives you the map reconstruction. When the signal-to-noise ratio decreases, the regularization has a stronger impact on the performance. You really improve when you have low signal-to-noise ratio compared to what does least square. So in this sense, the maximum a posteriori approach is really important. But this is okay if you have the correct prior statistics on your system. And if you don't, I have done first a theoretical analysis of this, which means that one in the maximum a posteriori estimator uses both priors on the turbulence trends and priors on the noise variance. And what you can do is suppose that you did not estimate these two correctly. So maybe you have put too much of a regularization or too much of data noise variance priors. And it gives you that you can estimate it with this hyperparameter, mu, and it gives a curves like this for the error you make in your reconstruction. So here, when mu is equal to 0, what you obtain here is you cancel the regularization, so you have a Gaussian least square estimator. And this is like the worst wavefront reconstruction you want to do. So it gives you the threshold, and you don't want to have a bigger error than this. And as soon as you will put regularization, you will bias your estimate. But if you do it until the right value, you will really optimize the reconstruction. And if you put too much of regularization, you start to become very far from the data you got. You only rely on things you have input, but which are not correlated to the data, and then you start to have very bad reconstruction. So there is an optimal which is equal to the map reconstruction. And this is the one you want to get. And for this, I've showed that for adaptive optics, you can allow an error of a factor 2 on the turbulence strength or the noise variance, which is illustrated here by simulations. So for several signal-to-noise ratio, which are the different curves, and you see that for high signal-to-noise ratio, you don't gain much applying the good regularization, but as soon as you have very bad signal to noise ratio, you can strongly improve the map reconstruction. Another case of problem if you input bad statistic on your estimator is for the laser guide star on the extremely large telescope. So the principle of the laser guide star is, as I said before, to generate an artificial guide star in the sodium layer of the atmosphere. But since we have a very large telescope, now this star is resolved. So you ended with, since the sodium layer is spread around 10 kilometers, you can see as from a parallax effect, as soon as you get far from the point you launched the laser, you can see an elongated image, an elongated star. So on the subaperture of the wavefront sensor, you have not circular spot, but you have elongated spot. So you lose a lot of accuracy in your data measurements in the elongated direction because the pixels are not scaled correctly with respect to the size of the image. So this is a problem. And here it's illustrated for central launching, which is the case when the laser launch telescope are behind the secondary mirror of the telescope. And if you choose another case, which is studied for the E-ELT, is to launch the laser from the side of the telescope here. And since then you have 42 meters of distance, and you have 2 times more elongation in the subapertures on the other side of the pupil, which is really an increase. It leads to a spot which is 1 arcsecond by 10 arcseconds, which is really a big loss of accuracy. So it's a strong disadvantage for side launching, and it's been studied seriously for the European ELT to decide where we must launch the telescope, the laser. Okay. So for this, it has been showed that usual reconstructor considers that the noise is isotropic, uniformly spread over the data, and also the same noise is applied on the x gradient and on the gradient of x and y. And this is not true if you look at this and you have the elongation, which is so important. You have correlations between the slopes error in x and y because of this elongation. And the error is much bigger when you have a large elongation than when you have a small spot. So the idea of the inverse problem approach in here is to model this non-uniformity and correlation inside the noise covariance matrix, which has not been done so far when we used a laser guide star. We did like for a natural guide star, considering that it's uniform and uncorrelated. So it changed only to change the noise covariance matrix, this one, into from a diagonal matrix to a block 2 by 2 diagonal matrix. So it's really nothing inside the instrumentor, but what has been shown, it has been shown for the reconstruction that if you have 3 laser guide stars you are looking at in the field of view, in the first case, if you launch from the central position configuration, which is behind the secondary mirror here, all the subapertures have the same geometries. They all receive, you have 3 wavefront sensors looking at 3 laser guide stars, but all the wavefront sensors have the same repartition of the noise. And if you launch from 3 different positions around the primary mirror, here and here and here, the 3 wavefront sensors will see the elongation differently. And it has been shown by my colleagues that if we take into account this non-uniformity, we improve seriously the wavefront reconstruction for side launching. In the first case, the curve in blue represents the wavefront error in the reconstruction with a radial profile. And so here is the pupil. Here you have the central obstruction. And then you have the wavefront error increasing when you go through the farther away from the center of the pupil. And if you use only a diagonal noise covariance matrix, you really have big reconstruction error when you are far away, when you have large elongated spots. But if you introduce the non-uniformity and correlation, you slightly improve the wavefront reconstruction. And for side launch, it's much, the effect is much bigger, because as you have 2 times more elongation, you really have much more noise when you are far away from the launching point. So if you don't take into account these correlations, you really have very bad reconstruction. And it's a disadvantage for side launch. But if you just introduce this correlation inside the estimator, you obtain even better reconstruction than for central launch, because you have a more uniform distribution of the information over the pupil. So those were 2 examples of how good reconstruction you can obtain if you model correctly the direct process with the noise statistics and the statistics of the parameter in your problem. So now I will talk about closed-loop full simulations and theoretical aspects about adaptive optics. And first, the problem with the European ELT adaptive optics system is the way you compute the commands. Because in existing AO system, the number of actuators, degrees of freedom you have to control is lower than 350. So it means that in real time, from around 1 kilohertz, you have to compute a matrix vector multiplication of 2 times n by of n by 2 times n, which scale as n squared operations you have to apply at this speed. And it's not extensible to adaptive optics on the 42 meter. If you do this, you will have 2 orders of magnitudes more to compute, at least. And it's not possible with the current processors we have. And if we rely on the Moore's law evolution of the processor, it will be anyway difficult. So we have to do something different to apply the command of the deformable mirror on an extremely large telescope compared to what we do in the currently existing system. So not only the estimation is important, but also the way you compute it, the algorithm. And for this, So during the European ELT design study, we have been working in collaboration with ISC and ESO to develop new algorithms for the reconstruction and the control, and comparing them to get faster algorithm than the classical, which is here. So the classical is a matrix vector multiplication you apply in real time. So it's the way they do it at ESO usually, and so it's the one which is implemented as a reference, because we really know well how it works, how it performs. And what we did is that we had to compare this reference with the new algorithms that were proposed. So one has been implemented from here by Sarmontilla, which is Fourier transform reconstruction, which is not the map approach that I presented before. It's another way to reconstruct the wavefront. And a third one, which is the fractal iterative method, with a slightly strange, different control than the integrator, which is usually used in closed loop. And this one I implemented it. And so we had a full and common bench, which is just a simulator. The simulator which is used at ESO for extremely large AO system, because it requires a lot of computation. So it's a cluster dedicated to this test. And we have been comparing the performance of the fast algorithm to the reference one in order to see if we propose a faster algorithm, will it be worse than the one we know and we are sure perform well, which is the matrix vector multiply. So in terms of number of operation, you can have a rough idea of how it performs. Here is the line of the matrix vector multiplication, the number of operations required to apply in a closed loop as a function of the size of the system. So sphere, which will be placed in the VLT, which is 40 by 40 system, you already have a strong difference between what does the MVM algorithm and the fast ones, which are here. And for the smallest ELT case, which is the SCAO case, which is 84 by 84, so far, it will be much bigger, the difference. So we have compared this algorithm in terms of quality of the reconstruction for SCAO case on Octopus, which is the name of the cluster at ESO. Just to give you an idea, what does the various algorithms? So the matrix vector multiplication, which is the reference algorithm, has already computed. I cannot see. Oh, yeah. Has already computed this matrix and stored it. And it only has to apply it to the data, usually in parallel, to get the wavefront. And to get the wavefront. And since you said it's in closed loop, so the data are residual data, and so you have a residual wavefront here, and you use an integrator in the control to apply the command on the deformable mirror. The same control is used for the Fourier transform reconstruction, but what is done is that you get the data and you pass it through Fourier transform to have the data in the Fourier space, and you apply a special filter in the Fourier space. This is very fast to apply, and what limits the velocity of the computation is just the Fourier transform. So since it's done with FFT, it's quite fast. And the last one is the one I implemented, is about moving the data in another space, which is fractal space, and you apply an iterative algorithm to estimate the wavefront. So these three were compared. I just provide here some results about changing the turbulence conditions we are observing. And so here is R0, which is, which is R0, which describes the turbulence coherence distance, and T0, which is the speed at which the turbulence vary above the telescope. So we have studied the long exposure strain in K-band. We obtained with the various algorithms in closed loop. And if we just plot the limits, theoretical limits, with dashed line, which is just the delay of the system and the fact that we cannot correct for an infinite precise wavefront, but just at the precision of the deformable mirror actuator space, which is the fitting, then we see that we are very close to this limit, and that mainly we have done several simulations, and we have concluded that the three algorithms performs really similarly in terms of quality. But the fast algorithm have the advantages that they go much faster than the matrix vector multiply. Okay. And another thing I have done recently is the extension of what I have showed about wavefront reconstruction with elongated spot, but this time with a full closed loop ground layer AO. So to check that in closed loop, the benefit we have seen to use the correlation of the noise is still significant when we use it in a closed loop AO system. So I modeled the noise elongation correlation in this 4 laser guide star GLAO system. In a GLAO system, which is important is the repartition of the turbulence in altitude, because since you just correct for the altitude close to the telescope, it has a strong impact on the performance. Yeah. Here is the profile of the turbulence in altitude. So you see that there is more than 50% of the turbulence which is lower than the first kilometer. And then above, on the right, it's getting less. So this distribution is strongly linked to the performance you will give later. An illustration of how side launch is degraded if you don't use the noise correlation is here with just one laser guide star. If you make like a SCAO closed loop with just one laser guide star on a 42-meter telescope, you see that side launch, even for very bright guide star, which means a lot of photons per subaperture, you have much less strain than for central launch. So it's a big disadvantage of side launching, and it's why the American, for the TMT, 30-meter telescope, they at the beginning decided to use central launch and to develop even radial detectors to be able to sample the elongated spot quite well. And they could not think about using side launching because of the strong elongation and because of this loss of performance. But in Europe, we have done the study of using this noise correlation in the reconstruction. So here is with the 4 laser guide star. In the central launch, all the subapertures see the same geometry of the elongation. And in the side launching, they all have a different distribution of the elongation. And in a closed loop system, we see that if we don't use the noise correlation, which is here with diagonal noise covariance matrix, then you, here it's the size of the 50% and squared energy for the JLAO correction. So since you go down, you improve your performance. For example, here is when you make nothing, you just don't have any correction, and you can reduce at high flux by a factor 2 or 4 in area the 50% and squared energy. And so when you have low flux, you degrade progressively the performance. And if you don't have the noise correlation, you see that the side launch again is performing less well than the central launch. And if you do this with the taking into account the noise correlation, this time side launch and central launch have no difference, significant difference in performance. And other aspects can be added to this because it's strongly related to the flux you receive, and it means that the requirements in terms of laser power will be changed. And if you can have the same performance at a given return flux of laser, means that you can build the same laser launch telescopes for side launch or central launch, and you will have the same performance. But which is important is that maybe if you launch from behind the secondary, you will have beam relay much more complicated than if you launch from the side of the telescope, and you can lose a factor 2 in laser power because of this beam relay. So it means that you will have it's simpler to launch from the edge for a given flux that you want to obtain back from the laser. So it's at the end it becomes an advantage to use side launch compared to central launch. And these GLAO simulations have been completed by laser tomography simulation done at ESO, which also shows that for diffraction limited correction, side launch and central launch can perform equally if you use the noise correlation due to the elongation. So it's really the way we have done this approach, modeling well the noise statistics, which really allowed us to say side launching of the telescopes is a good thing for the European ELT. Of course, it's not a complete study. There are other effects of side launching and central launch, but it's a major point. So, in conclusion, I try to show you some of the difficulties and the challenges of the European ELT adaptive optic systems. And I've presented what I've been working on, which is trying to obtain a good model of the wavefront reconstruction using an inverse problem approach. And we could see that modeling correctly the statistics we know can help the system in its performance. And it's not only for wavefront reconstruction, but it has an impact on the closed loop control and performance of the EO system. And it has had a major impact for the laser guide star system, trying to convince that people that side launch can be as good as central launch. Actually, at the TMT, they are now thinking about side launching. So And I want to thank the ELT design study and FP7, which have supported all these studies. Thank you for your attention.
Thank you very much, Clementine. We have time for questions, comments, suggestions.
I would have several questions. I'll just cut to two. Question number one is, this means that natural star adaptive optics is not foreseen at all.
No, yes, it's foreseen. The European ELT is supposed to be an adaptive telescope, which means that it has by default single-conjugate AO, which is done with a natural guide star, and also natural guide star GLAO, ground layer AO, correction. So it's foreseen. But for many, I would say, as far as I understood it, but you know the science case is better than me, I guess. Many of the science cases require laser guide star adaptive optics because there will not be bright guide star in the direction you want to observe. So it's like multi-object adaptive optics, which expect to study the dynamics of the galaxies. You will need this laser guide star. But it's still foreseen, but personally I don't know for which science cases.
My other question is, it's very nice that you've been doing all these simulations with octopus and everything. Mm-hmm. Fantastic. But is anybody thinking about putting these 3-4 lasers, like on the sides of VLT, for example, or is there any here, or on GTC, and try to see if actually this leads to a real advantage?
There is no exactly experiment like this as far as I know, but there is a bench in where there is a lot to do about this, about laser guide stars still, because we discovered with the ELT that it will be much more difficult to use than on the 10-meter telescope. And so in Canada there is a bench which is supposed to simulate the elongated spots and to compare really the performance of the system, but it's a bench, it's not on SCAO. And there are also several studies, much more accurate than what we had done before, about the laser sodium density in the sodium layer, because a lot of the performance of the adaptive optic system is strongly related to the way the laser density is evolving in time. And there is very, very few data with the right accuracy about this. So I think in the coming years there will be a lot of studies to really understand which performance we're going to have. But so far there is no plan, as far as I know, to put lasers on the side of the telescope. But it must be really far away to have this impact. It's because of the 30 or 40-meter telescope.
Well, no, I just wanted to make a comment that most likely for the colleagues astronomers that perhaps wasn't clear that the deformable mirror is neither the primary mirror nor the secondary mirror.
No, it's the fourth mirror.
All right.
Okay. Yes, it's true.
Because people keep thinking, oh, right, so we have M1, which is 42 meters, and is changing at 1 kilohertz.
No, M1 is just segmented, not deformable. Yeah.
Yeah, we have some more questions.
Yeah.
This is the question of a complete outsider, but the laser stars, these are sodium stars, so they are visible stars. They emit light in the visible, whereas the correction is in the infrared, 2 microns. You were talking about that. Would this be a problem?
Okay, no, it's not a problem at all. You can observe first the wavefront sensing. The Shakardman wavefront sensing is not achromatic. I mean, it gives you the same data, whatever the wavelengths you observe. So you are not, you don't have to filter wavelengths to get the data.
The properties of the atmosphere depend on wavelength. So if you get the properties of the atmosphere in the visible,
no, it's not. It's a problem of difference optical path, which is just this optical path is not depending on wavelength. The phase is, well, you can answer better than me.
The thing is, for usual or for standard EO systems like the ones presented here by Clementine, atmospheric chromaticity is not an issue. It will be an issue for an extreme adaptive optic system, but it is not the thing that Clementine was talking about. So basically, in the range from the visible down to K, the atmosphere is quite achromatic to make the function valid when saying that the correction you are measuring, the correction at the wavelength you are measuring and the correction at the wavelength where you are correcting is the same. Yeah. I mean, chromaticity of the atmosphere is only when you are trying to do corrections at the level of 95% astral or something like that with a 42-meter telescope. But the case where Clementine was talking about was 50, 60% in K-band. So it's very far, far away from the point when it becomes an issue.
Thank you.
Any other comments, suggestions? Then I think we should thank again Clementine for a very nice talk.